Hello and welcome to the video solutions here for this A-level maths predicted paper. Now I'm calling this a predicted paper. It isn't really a predicted paper as such, right? As you can see then, it is just a mock exam paper that we produced here at AJMaths. So this is set C, paper 1. We do also have set A and set B. You can also view those over on our YouTube channel, or you can download the papers from our website, ajmaths.co.uk. So before we jump into the paper here, there's just a few quick points that we need to make here. So this practice paper closely follows the Pearson Edexcel specification for A-level maths. However, Pearson Edexcel have no affiliation to this paper and are not responsible for any of the material featured in this paper. Of course, you can just use the calculator, and we also have 120 minutes to complete this paper, or 2 hours, right? Just your standard stuff. There's 14 questions in this paper, and of course, again, the total number of marks for this paper is 100, just as you would expect here from, a typical A-level maths exam. Other than that, there isn't really too much to say here. As I mentioned, right, if you want to download this paper, please do go and visit our website, ajmaths.co.uk. We also have worksheets, additional revision videos, all that good stuff, right? So go and check that out if you are looking for a little bit of an extra push here in the run-up to your upcoming A-level maths exams. And then finally, to finish with here, all I want to say, right, is best of luck for the upcoming A-level maths exams. I appreciate it's a very stressful time, but hopefully this predicted paper here and paper 2 and paper 3, when we release those very, very shortly, which will be soon, by the way, and will hopefully help in your A-level maths exam preparation. So other than that, I am waffling a little bit here. So best of luck for the upcoming A-level maths exams. And let's just get started then with question 1 here. So let's just make a start here then with question 1. So as we can see then for question 1 here, quite a nice easy question just to get us started, right? Just on the small angle approximations. What I've also included here in the top right corner is the relevant results then for the small angle approximations as they're given in your formula book. So what do we have here then for question 1? So what I'm given here then is that theta is small and measured in radians, and all we want to do here then is just use the small angle approximations to show that this equation here, equation 1, can be written as follows. So starting off then with part A here. So like we said then, hopefully nice and straightforward here, right? All we need to do then is just use the small angle approximation. So straight away, I can see that we have sine and cosine, but no tan here, okay? So let's just begin here then by crossing off this approximation, right? Because we won't need this approximation here at any point in this question. So if I've got sine 2 theta here, using this approximation then, just replace your argument here with 2 theta. So sine 2 theta would be approximately 2 theta, okay? So we've got 2 theta. We then have minus cos 3 theta. So again, all I need to do here is replace the argument of our trig function here with 3 theta. So in that case then, what I get here is minus. So we get 1 minus then. So replacing theta with 3 theta. And we square the full thing, by the way. I get 1 minus 3 theta squared over 2. Okay, so we've also got 7 theta here. So plus 7 theta. And all of this here is equal to minus a half. So minus 1 over 2 there. Okay. So let's just simplify the left-hand side here. So 2 theta plus 7 theta, nice and straightforward. Then that is 9 theta. I've got minus 1. And then minus of a minus here, so this becomes positive. So 3 theta all squared is 9 theta squared. I get 9 theta squared over 2, like so. And this here then, this is my left-hand side, is equal to minus a half. Okay. Now, what I want here then is 9 theta squared. So I want the coefficient here of theta squared to be an integer. So let's just times through then by 2. So if we do that here then, what do we get? I get 18 theta. So 18 theta minus 2 plus 9 theta squared is equal to minus 1. Make sure you do it to both sides, right? And then finally, let's just make the right-hand side here equal to 0. So let's just add 1 to both sides. And in that case, then what we get here is 9 theta squared plus 18 theta. So plus 18 theta, and then minus 2 plus 1 gives us minus 1 here. And all of this then is equal to 0, right? Exactly as we require here. Okay, so as required there, and that gives us the solution to part A. So as required. And now for part B then, what do we have here? So what we're told here then is the solutions of this equation here. Just notice that's the exact same, right, as what we just derived here in part A. So the solutions of this equation here are given as theta is equal to 0.0541 and theta is equal to minus 2.05, each correct to 3 significant figures. So for part B then, as we can see, right, just 1 mark for this, so we shouldn't really expect too much work here. All we need to do then is just comment on the validity of each of these values as solutions to this equation here. Now, what you're looking for here then is whether theta is small. Now, clearly, this value of theta here is small, right? It's close to 0. So, theta is equal to, so it's 0.0541 is small. So therefore, this value here, okay, would be valid. So theta is equal to 0.0541 is small. So therefore, valid as a solution. So valid as a solution. However, this value of theta here, right? So theta is equal to minus 2.05. That isn't small. So if you substitute that value here of theta into this equation here, you'll find that it's not a very good approximation. However, if you substitute this value in here, you'd find that this is a pretty good approximation, right? And feel free to try that if you want to. Obviously, in an exam, you're not really going to get the time to do that, but just as a bit of practice, you can kind of do that and see what happens, okay? So theta then is equal to minus 2.05. Oops. So minus 2.05 is not small. So therefore, not valid. So not valid as a solution. Okay. And there we have it then. So that's all we need there for question 1. Hopefully nice and easy. So let's just have a go then at question 2 here. So straight away then for question 2, I can see that we have figure 1. And figure 1 then shows a sketch of part of the curve with this equation here. So y is equal to f of x. We've also got this table here, and this table then shows corresponding values of x and y for this curve between x equals 0.6 and x equals 1. And we can see that here then, again, on figure 1. So for the first part of this question, part A, what we want to do here then is just use the trapezium rule with all the values of y in the table above to obtain an estimate for this integral here. So starting off then with part A here, hopefully nice and straightforward, right? Because it's just simply an application of the trapezium rule. And don't forget as well, the trapezium rule here is also given in your formula book. So what I've got here then is the integral of f of x. So the integral of f of x here with respect to x from 0.6 to 1. Okay. And by the trapezium rule then, this will be approximately. So to begin with, we have h over 2. So h here is simply 0.1, right? 0.7 minus 0.6 is 0.1. 0.8 minus 0.7, again, is 0.1. So h here is 0.1. So I get 0.1 divided by 2. And what I do here then is I times this by the following. So I've got y0 plus yn, so that's my first y value plus my last y value. So that is going to be 3.095. That's my first y value, 3.095, plus my last y value. So plus 3.414. I then have 2 lots of everything else. So 2 lots of, so what have I got here? So 3.183. So 3.183 plus 3.265, 265, and then also 3.342. Apologies, I've kind of run out of room here at the top. So 3.342 there. Okay. So 2 lots of this summation here. So 3.183 plus 3.265 plus 3.342. We times that sum here by 2. add on these two terms here, so 3.095 and 3.414, or these two y values, whatever you want to call that, and then we times that by 0.1 divided by 2, right? All you need to do then is just put this into your calculator. And if you do this correctly then, what you should find here is we get 1.304 there, okay? I should have put here, give this to 4 significant figures. I'll just mention it there. So 4 significant figures there, okay? And there we have it then. So nice and straightforward. That gives us the solution to part A. Now for part B then, so for part B here, again, nothing too challenging. All we want to do here then is use the answer to part A, that was this result here, this integral, to estimate the value then of this integral here. So what do we have then for part B? So what I've got here then is the integral of, I've got 3 plus 5 of x. Okay, like so. And again, integrating here with respect to x. And again, the limits are the exact same as what we had in part A. So 0.6 to 1. Okay. So what I'm going to do here then is split my integrand up into 2 separate integrals. So what I've got here then is the integral of 3 with respect to x from 0.6 to 1, and also the integral then of 5 f of x. And again, integrating here with respect to x from 0.6 to 1. Okay, so this integral here then, nice and straightforward, that is simply 3x. I'll come back to the limits in just a moment. 0.6 to 1. Now, this integral here, what I can do then is apply linearity and take the 5 outside the integral. So this is 5 lots of this integral here of f of x, which we evaluated in part A, right? That's going to be 5 lots then of the result that we obtained in part A. So 5 lots of 1.304. Okay. So this here then is going to be 3 times 1, which is 3. To get 3 minus then 3 times 0.6, which is 1.8, plus 5 lots of this here. So 5 lots, again, of 1.304. Again, what you need to do here is just put this into your calculator. And if you do this correctly then, what you should find here is we get 7.72 there. Okay. And there we have it then. So this here is the solution to part B. That is the, estimated value of this integral here from 0.6 to 1, 7.72 there. Okay. And there we have it then. So that gives us the solution to question 2. Now for the next question here, question 3, as we can see them, quite a small question, right? There is just the 5 marks for this question here. So what I've got then is figure 2 below. So as we can see then, figure 2 here shows a sketch of the curve with this equation here. We're told that the curve cuts the x-axis at 2 points, A and B, again, as we can see on figure 2. Now for the first part of this question, then part A, let's just write this at the top here. All we want to do then is show that the x-quant of A here lies in this interval. So that's for this point here, right? So what I want to show then is basically there is a change of sign in this interval here because this function then is continuous, right? So to begin with here, let's just rewrite this equation here as a function. You don't have to, but I just think it makes the notation a little bit easier as we work through this question. So in that case then, f of x here is equal to, so it's 2 ln of x plus 1. So 2 ln of x plus 1 minus 1 over 4 x squared plus 1. Okay. So what we need to evaluate here then is f of minus 0.4 and also f of minus 0.3. Like so. Okay. So nice and straightforward then, just simply substitute minus 0.4 and minus 0.3 into this function here, right? Just use a calculator. So if you do this correctly then, what you should find here for f of minus 0.4 is we get minus 0.061651 That just keeps going on and on and on. So this here then, hopefully you can see straight away that this is less than 0, right? What we'd expect then for f of minus 0.3 here is we get a positive value, okay? And if you do this correctly then, what we should find here for f of minus 0.3 is we get 0.2615. Again, that just keeps going on and on, right? But clearly, this is greater than 0. Perfect. So what we've got here then is a change of sign, and the function is continuous over this interval. So let's just make a note of that here. So we have a change of sign. And the function is continuous. We have a change of sign and the function is continuous over the interval. So therefore, in that case then, the x coordinate, the x coordinate of A here, that's this point here, the x coordinate of A lies in the given interval. So it lies in the interval from minus 0.4 to minus 0.3. Perfect. Okay. Now, this might seem a little bit excessive here, given such a, a large conclusion, but it is necessary, right? It's important that we state that we have a change of sign and also that the function is continuous. This is really, really important. If you don't do this, you are going to lose a mark, right? And then finally, in that case, if we have a change of sign and the function is continuous over the interval, in that case, then the x1 of A lies in the given interval. Okay? So there we have it then. Hopefully nice and straightforward there for part A. And now for the second part of this question here, part B. Well, as we can see then, this is split into two different parts. So for the first part then, part 1, well, what we're told here, so we're told that the point B can be found by using the iterative formula here. Xn plus 1 is equal to the square root of A ln xn plus 1 plus 4, with x1 equals 4. So we want to find then for the first part anyway, the value of x2, giving your answer to 5 decimal places. So there's two ways to do this. You can just do it by hand. That's absolutely fine. But for the second part of part B here, as we can see then, it is basically continued iteration, or it is continued iteration. So at this point here, it's just much easier to use a calculator, okay? And I would always personally recommend using a calculator for iteration questions, just to save a lot of time, okay? So how does this work here? Well, the first thing that I do then is I input x1 equals 4 into my calculator. So all I do then is input 4. And what that does here then is it saves 4 into the memory of my calculator, okay? So I input 4, I press enter or execute in my case, my calculator. Let's just exit like so. Now, for the next step then, what I need to do here is input the iterative formula and basically just replace any xn's with answer, okay? So on my calculator here then, this will look like the following. So put all of this here inside a bracket just so there's no errors here with the square root. So it's 8 ln. So A ln. Now inside the bracket here, I've got an xn to replace xn with answer. So it's going to be the square root here of 8 ln bracket. So it's answer. Don't forget the plus 1 as well inside the bracket. Answer plus 1. And don't forget as well, plus 4 here. Like so. Okay. Obviously, don't forget to close those brackets. Perfect. So let me just quickly input that then on my calculator here. So A ln bracket, so it's answer plus 1, close that bracket, plus 4, close the final bracket. And now again, press execute here. And what that gives me then is x2 here. So therefore, x2 then, how many decimal places is this 2? So to 5 decimal places then, what I'm going to get here is 4.107 0.98 there. Okay. If you press enter again, that would give you x3. Press it again, that's x4. Again, x5, so on and so on, right? But we only want x2 here. That's absolutely fine. And now for the second part then, as we mentioned before, this is for now continued iteration. So we want to find then by continued iteration, the x quant of b, giving your answer to 4 decimal places. So basically all we need to do here then is just spam the execute button or enter button here, or calculate button, whatever it is on your calculator, right? And basically what's going to happen here then is this is going to converge to the root here, right? The point B. So just press enter a load of times here, nothing fancy, right? And what you'll find then is eventually your calculator just keeps giving you the same value, okay? No matter how many times you keep pressing it, you'll get the same value. And at this point here, it's now converged to the root here, okay? So on my calculator here, and you should get the same if you've inputted this here correctly, is then that x is equal to, this is to 4 decimal places here, right? So just be careful for the accuracy. So what I get here then to 4 decimal places is 4.1336 there. Okay, and again, that is to 4 decimal places. Okay, but there we have it then. Hopefully nice and straightforward there for question 3. And that gives us the solution to question 3. So for the next question here, we now have question 4. And as we can see then for question 4 here, this is on vectors. Now vectors is a topic that not many students actually enjoy. But to be honest, for 5 marks, this question is pretty decent. So what I've got here then is the vectors AB and BC, and they're given as follows. We're also told that P and Q are constants, and we're also given here that the vector AC is parallel to this vector here. And all we want to do then is just find the value of P and Q here. So to get us started here then, let's just find the vector AC here. So the vector AC then, well, this here is the vector AB, and this here is the vector BC. So if I want the vector AC, that would just simply be the sum of these 2 vectors here. That's the vector AB plus the vector BC. Okay. In that case then, what do we get here? So I've got 6P and 2Q. Like so. Plus the vector BC. And BC here then is giving us 4 minus Q and 3P. So 4 minus Q and 3P. Okay. So nice and straightforward here then. What do we get? So 6 plus 4 is 10. P plus minus Q, well, that's just simply P minus Q. And then finally 2Q plus 3P. Well, let's just write that in alphabetical order here as 3P plus 2Q. Okay. And this here then, this is the vector AC. Now what we're told here then is this vector, the vector AC, is parallel to this vector here. And what that means then is this vector here times by some scalar must be equal to this vector here, right? Because they're parallel. So what I've got here then is lambda, just some scalar, right? Times by this vector here, 2, minus 1, and 4, must be equal to this vector here. This is the vector AC, right? So 10, P minus Q, and then finally 3P plus 2Q. Okay. Now I am hoping that's obvious here what the value of lambda must be, but just in case it's not right, well, 2 lambda is equal to 10, and in that case then lambda is equal to 5. Okay. And if lambda is equal to 5 then, what we can now do here is form simultaneous equations, right? Because minus 1 times lambda, well, lambda is equal to 5, so minus 5 then must be equal to P minus Q. What we've got here then is P minus Q is equal to minus 5. And again, over here, times by lambda, well, lambda is equal to 5, so that's 20. must be equal to 3p plus 2q. So 3p plus 2q is equal to 20. All we need to do here then is just solve these simultaneous equations, right? Should be nice and straightforward. This is just, basic GCSE maths simultaneous equations. So let's just times this one here by 2. If we do that then, what do we get here? To get 2p minus 2q, so 2p minus 2q is equal to minus 10. Obviously, the bottom equation here doesn't change. So 3p plus 2q is equal to 20. Just add these two equations together here. So what does that give us here then? 2p plus 3p is 5p. They just cancel. And then minus 10 plus 20, that gives us 10 here. So 5p is equal to 10. Nice and straightforward then. P must be simply equal to 2. And once we obtain the value then of one of these constants, p or q, we can easily solve for the remaining constant. So if p is equal to 2 here, then let's just rearrange and make q the subject. So q then, from this equation here, q is equal to p plus 5, like so. In that case, then q is equal to p, which is 2, plus 5, so 2 plus 5, which is equal to 7. Okay, so to finish with then, we've already found them, but let's just state the values then of p and q. So therefore, p is equal to 2, and q here is equal to 7. Okay, and let me just highlight that here then. So this here is our solution for question 4. Okay, and there we have it then. So like we just said, right, that gives us the solution to question 4. So moving on to question 5 then, where we have a question here on exponential modelling. So for this question here, it's absolutely riveting stuff. We've got the temperature T degrees Celsius of a room, and that's related to the time T in minutes since the heat source was turned off by the following model. So A and B here are constants. We're given that the temperature of the air in the room is, so it's 20 degrees Celsius the instant that the heat source is turned off, and 15 degrees Celsius exactly 30 minutes after the heat source is turned off. So for the first part of this question, part A, all we want to do then is find a complete equation for the model, given the value of B to 3 significant figures. Right, so for part A then, where do we begin here? So to begin with here, let me just start by writing down T as it's given here. So T is equal to, so it's 12 plus AE to the minus BT, okay? And this is for T greater than or equal to 0, okay? Well, what I'm told here then is this first fact here, that's when T is equal to 0. And then for this second fact here, right, that is when T is 30 minutes after the heat source is turned off. Now when T is equal to 0, the temperature here T is equal to 20. So T is 20. And then when T is equal to 30, T is 15. Okay. So to begin with here, let's just substitute T equals 0 into this model here, right? So when T is equal to 0, what do we get here then? So we know the temperature is 20, so I get 12 plus AE. So to the minus B times 0, so that's just to the power of 0, right? Like so. And all of this here is equal to 20. Okay. Now, e to the 0 is just 1. So I've got 12 plus A is 20. Nice and straightforward. Then A here is simply A. Okay, so nice and straightforward there. That gives us the value of A. And we also need to find the value of B then, right? If we want the complete equation for the model, we also need to find the value of B. We're going to give that to 3 significant figures here. So to find the value of B then, we're going to use this second fact here, right? When T is equal to 30, the temperature is 15 degrees Celsius. So let's just do that underneath them. So when t is equal to 30, what do we get here then? So I get 12. We now use the fact that a is equal to a. So I get 12 plus ae to the minus then b times by t here, which is 30. And we know then that this here is equal to 15. Like so. So let's start by subtracting 12 off both sides. So I get ae to the power then of minus 30b is equal to 15 minus 12, which is 3. We now divide both sides by 8, right? So e to the power then of minus 30b is equal to 3 over 8. Like so. And then at this point here, right, we're pretty much done. We just need to solve for b here. So get the natural log of both sides then. I'm also just going to divide through by minus 30 as well at the same time. So in that case then, we find that b here. So b is equal to minus 1 over 30 times by the natural logarithm then of 3 over 8. So learn of 3 over 8 there. Okay. Now, it did ask for this to 3 significant figures here. So I didn't actually do that myself. So let me just quickly grab my calculator. So minus 1 over 30 times natural logarithm of 3 over 8. So 3 significant figures. Then what do I get here? So I get 0.0327. So 0.0327 there. Perfect. Okay. So let's just state then the complete equation for the model, right? So therefore, the full model. So the full model is, so it's t is equal to 12 plus ae to the minus bt. So that's a is 8 here, right? So plus ae to the minus bt would be here is 0.0327. So the minus then 0.0327 t there. Okay. And there we have it then. So that gives the solution to part A. That's the first 4 marks in the bag. Now for the next part of the question here, then part B, it just says using the values of A and B that you determined in part A, find, according to the model, the rate of change of the temperature of the air in the room exactly 15 minutes after the heat source is turned off. Again, like I said, right, really riveting stuff here. So for part B then, I should have just about enough room here underneath. So for part B then, well, as soon as you see this kind of phrase here, rate of change, this should be jumping out at you then to differentiate. Okay, so differentiate here. So what are we differentiating here? Well, what I'm differentiating then here is the temperature T with respect to time T. So it's a derivative then. It's not going to be the prettiest, but it's going to be d capital T over dt with a little t, right? This is the derivative of t here with respect to little t, time, right? So it's just the rate of change for the temperature with respect to time t. Okay. So what I'm going to do here then is differentiate this model here. Shouldn't be anything too challenging, right? The 12 here is just a constant, so that differentiates to give me 0. I then get 8 times minus 0.0327 e to the power then of this here. So, like we just said then, it is minus 0.0327 times by ae to the power then of minus 0.0327 t there. Okay. Now, what I want to do here then is find the rate of change of the temperature of the air in the room exactly 15 minutes after the heat source is turned off. So what that is telling me here is that little t is 15. Okay. So what we now need to do here, right, is just substitute t equals 15 into this derivative here. So I'll just make a note then. So when t is equal to 15, what I get here then is the derivative of t with respect to little t when t is equal to 15. That is given as, so it's minus 0.0327 times ae to the power then of minus 0.0327 times 15. Okay, so let's just write that down in full then. So minus 0.0327 times by ae, the power then of minus 0.0327 times by t here, which is 15, right? And that by 15. At this point here, just use a calculator. So what I get here then is minus 0.16 here, okay? So what that's telling me here then is the rate of change here of the temperature of the air in the room exactly 15 minutes after the heat source is turned off, right? It's telling me here that this is decreasing at a rate of 0.16 degrees Celsius per minute, okay? Let's just state that here. So therefore, decreasing. So it's decreasing at a rate of 0.16 degrees Celsius per minute. Okay, and there we have it then. So that gives the solution to part B. And then finally, for the very last part of this question here, part C, it just says briefly explain why, according to the model, the temperature of the air in the room cannot drop to 8 degrees Celsius. So I don't have a lot of room here, so let me just quickly box off, do it in green, the bottom right corner here, just so I can answer part C. It's just 1 mark, right? We don't really need too much for this. So if you look at the model here, well, I'm hoping it's kind of obvious here that the temperature has a lower limit of 12 degrees Celsius here, right? Because this here, this AE to the minus 0.0327t, this is always greater than or equal to 0, okay? So no matter what, my lower limit here for the temperature must be 12 degrees Celsius. So let's just make a note here. So the temperature has a lower limit of 12 degrees Celsius there. Okay, this was for part C, by the way. Apologies. Just stated at the beginning, but there you go. Alternatively, what you could also say here, and you don't need both of these comments, by the way, but just in case you might find this one easier, is as t, so little t here, tends to infinity, then capital T here, the temperature, tends to 12. Okay, again, just stating then that the temperature here has this lower limit of 12 degrees Celsius. Either of these is absolutely fine. Just make it clear then that you kind of, understand why, according to the model, it can't drop to 8 degrees Celsius. But yeah, there we have it, right? So again, it's just 1 mark. You don't need tons there. It would be absolutely fine. So there we have it then. That gives the solution there to question 5. So for question 6, then we want to prove by contradiction that the curve of this equation here has no stationary points. Now, given that this is a proof by contradiction here, we should always just start then with an opening assumption. Now, for my assumption here, I'm going to assume the opposite. So what I'm going to assume here then is that the curve with this equation here does have a stationary point. So in that case then, the curve has a stationary point. The curve has a stationary point. And in that case then, so if the curve here does have a stationary point, we know then that dy by dx here must be equal to 0 for some value of x. Or some value of x here. Okay, so to begin with here then, let's just find dy by dx, set that equal to 0, and then hopefully we do arrive at some kind of contradiction here. So for dy by dx here then, hopefully nice and straightforward, just go term by term, right? So the 2x cubed that differentiates to give us 6x squared. The 3x here, that differentiates to give us plus 3. And now the minus sine x here, that differentiates to give us minus cos x. Okay. As we said then, as part of the original assumption here, dy by dx must be equal to 0 for some value of x. So let's just set dy by dx here equal to 0. So if we do that underneath then, what do we get here? I get 6x squared plus 3 minus cos x is equal to 0. And at some point here, we need to arrive at a contradiction. And I think the easiest way here to derive the contradiction is to take this minus cos x here over to the other side. So again, if I just do that underneath here, what do we get? So we get cos x is equal to 6x squared. So 6x squared plus 3. And hopefully the contradiction here is clear to see now, because on the right-hand side, well, the 6x squared here must be always greater than or equal to 0. So no matter what, then my right-hand side here must be greater than or equal to 3. Okay. And for the left-hand side here then, well, this is cos x. So cos x is between minus 1 and 1, right? And in that case here, then we have a contradiction. This equation here doesn't hold, right? So therefore, we have a contradiction. So we have a contradiction. So let's just try and briefly explain this contradiction here. So we have a contradiction because my right-hand side here, as the right-hand side then, must be greater than or equal to 3, right? As we mentioned before, this here is greater than or equal to 0. So no matter what, my right-hand side is greater than or equal to 3. And then for the left-hand side here, and the left-hand side, so for the left-hand side here then, what did we say before? So the absolute value then, or the modulus here, of cos x, this is less than or equal to 1. So cos x then is between minus 1 and 1. Okay. Just in case you find it easier like this. Just the same thing. So cos x is between minus 1 and 1 here. Okay. So what happens here then, or what we've kind of arrived at, is we've disproved the original statement here. Okay, my original assumption. So in that case then, the original assumption is false. And in that case then, the curve with this equation here will have no stationary points. And the curve with equation then, y is equal to 2x cubed plus 3x minus sine x has no stationary points. Okay, it has no stationary points. And there we have it then. So bosh, proof complete. Okay, so there we have it then. Hopefully nothing too challenging there. I know many students don't really enjoy proof by contradiction, but to be honest, for 4 marks, I don't think that's too bad, right? So there we have it then. That gives us the solution to question 6. So moving on to question 7 then, where, as we can see, right, we just have a question on functions. So the function g of x is defined as follows. So g of x is equal to 2x squared minus 1, for x belongs to a set of real numbers, and x is greater than or equal to 0. So for the first part of this question, part A, all we want to do then is just state the range of g of x, right? So pretty straightforward. And as we can see then, just 1 mark for this part of the question. We shouldn't really be expecting too much work here. So for part A then, I think the easiest way to do this is just draw a quick sketch of g of x. So I've got my y-axis here. It doesn't need to be perfect, by the way, right? Just so we can identify the range here. I've also got my x-axis here, like so. So if I want to sketch this function here, now just be slightly careful, right? This is defined for x belonging to the set of real numbers and x is greater than or equal to 0. So normally, if I was to sketch this quadratic here, this is just a positive quadratic, so it's going to have kind of U shape like that. However, because it's defined just for the positive integers, well, sorry, not positive integers here, let's just be slightly careful. X belongs to a set of real numbers, but x is greater than or equal to 0. So we don't have any negative x values here. So if I was to sketch this here, normally it would look, say, something like that, right? However, like we just said, we have no negative values of x here. So let's quickly erase that. It would look, say, like this. Okay. But this point here is the point of intersection then for this curve and the y-axis, which in this case here is just simply -1. Okay. And in that case then, the range here, so the range then is g of x is greater than or equal to this point here of -1. Okay. So hopefully nice and straightforward there then for part A. Now for part B then, what do we want to do here? So we want to show then that this composition of functions here, g of x, is equal to the following quartic. So normally here we do need to be careful when we have a composition of functions, right? Now we've got the correct order. But in this case here, because it's the composition of the same function, g of x, obviously the order doesn't matter. So for g of x then, all we need to do here is just replace then any x's here in g of x with g of x. So if I do that here then, what I get is two lots. So two lots of x squared here. So two lots of g of x squared. So two lots then of 2x squared minus 1. Don't forget that we square this here. And don't forget as well the -1. And at this point here, it's just a matter of expanding, simplifying, and hopefully we obtain this here. So I get two lots then of, so expanding these double brackets here, then I get 4x to the 4. So 4x to the 4. I get 2x squared times -1, so that's -2x squared. We also repeat that again. So in total, I've got -4x squared. So -4x squared. And then finally, -1 times -1 gives us +1 there. Like so. Again, don't forget the -1 here. It is really easy to kind of forget that as you work through the question. And then we just expand here, this bracket with the 2. I get 8x to the 4. I get -8x squared. So -8x squared. 2 times 1 is 2. If I subtract 1, I'll just get 1, right? And in that case here then, g of x is equal to this here, 8x to the 4 minus 8x squared plus 1, exactly as we require, right? So as required there, and that gives us the solution to part B. So as required there, hopefully nothing too challenging, right? Now for part C then, it says hence or otherwise solve g of x is equal to 17. So to begin with then, let's just set here g of x equal to 17. We get 8x to the 4 minus 8x squared plus 1 is equal to 17. Okay. Now, if I want to solve this quartic equation here, let's just start then by subtracting 17 off both sides, right? Basically, all I want to do here then is just make one side of the equation equal to 0. So subtracting 17 from both sides then, I get 8x to the 4. I get minus 8x squared. And I've got 1 minus 17, which gives us minus 16. And all of this here is equal to 0. Now what I can do here then is just divide through by 8, right? So if I do that, I get x to the 4 minus x squared minus 2 is equal to 0. Okay? What you need to recognize here then is at this point here, we have a disguised quadratic. Okay? So if you want to use a substitution, you can. If you want to just go ahead and factorize this, again, that's absolutely fine. What I will do here is I'll use a substitution just so you can see the full working here. So if I let y then, so let y be equal to x squared here, then what do I get? So this here is x squared squared, so that's just y squared. Let's do it underneath them. I just say then we get y squared. This here is just minus y. Minus 2 is equal to 0. And at this point here then, we now want to solve this quadratic equation, right? You know, generally speaking, a lot easier than this quartic equation here. So if I factorize this here then, what do I get? I get y minus 2 times y plus 1. And this is equal to 0. So I get two solutions here. We get that y is equal to 2. And I also get that y is equal to minus 1. Now, don't forget then, we're not solving for y here because y is equal to x squared. So let's just, reverse that substitution and replace y with x squared. So in that case then, x squared is equal to 2, and x squared here is equal to minus 1. So x squared being equal to 2, well, that gives me two solutions here. X then is equal to plus or minus root 2. I'll come back to this in a moment. Don't worry, I haven't made a mistake just yet. So I'll come back to that in a second. This one here, well, I can't solve this for x, right? As an A-level further maths student, you'll discover how we can solve this. But for A-level maths, we just say that there is no real solutions here. Okay, so for this bit here, I'll do it in a different color. Let's do it in red then. We just say here, no real solutions. Okay, so don't worry about that one. So going back to this solution here then, what was we saying, right? Well, we can have both of these here, and there is a reason for that, because just going back to the original function given here, and these conditions here, x belongs to a set of real numbers, but x must be greater than or equal to 0. So this solution here, that x is equal to minus root 2, we can't have that. So let's just get rid of the plus and minus here, like so. So x is just simply equal to root 2 there. Okay. In that case then, the GG of x is equal to 17. X here is equal to root 2. Okay. And there we have it then. So solving a quartic equation there, hopefully not too challenging. And then for the very last part of this question here, part D, we want to find this inverse function. And again, shouldn't really be anything too challenging here. So for G inverse of x here, where do we begin? So I'm just going to start here by writing down then y is equal to 2x squared minus 1. So y is equal to 2x squared minus 1. Okay. And what we want to do here then is rearrange and make x a subject. So I'm going to start by adding 1 to both sides. So 2x squared is equal to y plus 1. Like so. Let's just divide through by 2. So x squared is equal to y plus 1 over 2. And then finally here, we would normally just say that x is equal to, so x is equal to plus or minus the square root then of y plus 1 over 2, right? However, again, x here must be greater than or equal to 0. So the negative solution here, we wouldn't have that, we'd omit that, okay? So therefore x here, so x then is equal to the square root here of y plus 1 over 2. And then if we give the answer here as an inverse function, this is for G inverse, right? Therefore, G inverse of x here. So to finish with then, all we do here is replace x with g inverse of x, and replace any y's then with x here. Nice and straightforward, right? Don't forget, we did cover all of this, as part of basic A-level maths, and also you probably should have done this in GCSE maths as well, so hopefully nothing too challenging again. So what I get here then is the square root of x plus 1 over 2, okay? And there we have it then. So that's the solution to part D. This here is the solution to part C. Part B was a show that, and for part A then, nice and straightforward, okay? But there we have it then. So that gives us the solution here to question 7. So let's just have a go then at question 8 here. So for question 8 then, we're told that the path of a professional skateboarder from the point of leaving the ramp to the point of landing is defined by the following parametric equation. So clearly, this question here is looking at modeling with parametric equations. We're told that x measures the horizontal distance in meters from the point of leaving the ramp, and y is the height in meters above ground level of the skateboarder after t seconds. So for the first part of this question, then part A, what we want to do here is find the initial height of the skateboarder. And as we can see then, just one mark for this, we shouldn't really be expecting too much work, right? So for the initial height then, well, straight away, if we're talking about height, that's to do with y here, because y is the height in meters above ground level. And for the initial height then, well, that's when t is equal to 0. Okay, so all we need to do here is substitute t equals 0 into this equation here. So nice and straightforward then, y here is equal to, well, minus 4.9 times 0 squared is just 0. 3 times 0 is also 0. We just get y equals 6 here. And in that case then, what that tells us here is the initial height. So the initial height here is simply 6 meters. Okay, nice and easy then. That gives us the solution to part A. Now for the next part of this question, then part B, what do we want to do here then? So we now want to find the value of k and state the time taken for the skateboarder to complete the jump. So the value of k here is the upper bound for the time t. So k then is the point of landing. And the point of landing then is when y equals 0. So when y equals 0 here. Okay, so set y equal to 0 then. What I get here is minus 4.9 t squared plus 3t plus 6 is equal to 0. Now to make life a little bit easier then, let's just take everything over to the other side. To get 4.9 t squared minus 3t minus 6 is equal to 0. And what I want to do here then is just solve this quadratic equation for t. Now clearly, I can't solve this by factorizing, right? So I either need to use a quadratic formula or just use a calculator. Either's fine, but I'll show you how to do this then by using the quadratic formula. So we're solving for t here. So what do I get here then? So t is equal to, so I get 3 plus or minus then, the square root here of, so I get minus 3 squared, sorry. So minus 3 squared. So b squared, that's minus 3 squared. Minus then 4 times a, which is 4.9, times by c, which is minus 6, right? To the square root of the full thing here. And this then is all over 2 times a, where a is 4.9. So 2 times 4.9 there. Okay. If we simplify this here, then what do we get? So we get 3 plus or minus then the square root here of 126.6, like so. And this here then is all over 9.8. Okay. And this here then will give us two solutions, right? The positive solution and also the negative solution here. So what I get here then is that t is equal to 1.45 and also that t is equal to, so we get minus 0.8 over 2. Now t then is time, so clearly t cannot be negative, right? So we omit the negative solution here, and in that case then t is equal to 1.45. So let's just make a note here then that it takes So it takes 1.45 seconds to complete the jump. 1.45 seconds to complete the jump. Oops. So to complete the jump. And in that case then, k here is this value of t. So k then is equal to 1.45 there. Okay. And there we have it then. So that gives the solution to part B. Now for the next part of this question, part C, what we want to do here then is find the horizontal distance that the skateboarder jumps. And again, just one mark for this here, so we shouldn't really be expecting too much work, right? So for part C then, let's just do this underneath here. So what do we need to do here? So all I'm going to do then for part C is substitute this value of t then, 1.45, into this equation for x here. Now, rather than substituting t in this form here, it's better to substitute it in its exact form, right? So in that case, then what I get here is that x is equal to 16 times by the exact form here. So 3 plus the square root of 126.6 over 9.8. So 3 plus the square root then of 126.6, like so. And that's all over then 9.8 here. Okay. Just put this here then into your calculator. What we should get here then is 23.3. So this here then is the horizontal distance in meters from the point of leaving the ramp. So therefore the horizontal distance is 23.3 meters there. Okay. And there we have it then. So that is the solution to part C again. Nice and straightforward, right? And now for the final part of this question, then part D, as we can see here, there's 5 marks for this part of the question. And there is a bit of work involved here. And as we can see, right, we don't have a whole lot of room. So let me just quickly pause the video, clear the screen, and then we can have a go at answering part D. So as we can see, then we've now cleared the screen here. So let's just have a go then at answering part D. So for part D then, what do we want to do here? So we want to show then that the skateboarder's path is a parabola and also find the maximum height above ground level of the skateboarder. So to begin with then, if we want to show that the skateboarder's path is a parabola, how do we do that? Well, what I'm going to do here is rearrange equation 1, that is x equals 16t, making t the subject, and then substitute that into this equation here for y. Let's just call that equation 2. So rearranging equation 1 then, making t the subject, what do I get here? In that case then, nice and straightforward, right? T is equal to x over 16. Okay, let's just call this equation 3. So what we now do here then is substitute equation 3 into equation 2. In that case then, what I get here is y is equal to, so it's minus 4.9 times by t squared. So t here is x over 16. That is x over 16 whole squared, like so. Plus 3 lots of x over 16. So 3 lots of x over 16. And then finally, plus 6. Okay, so let's just clean this up a little bit here. What do we get then? So y is equal to, so 16 squared is 256. So I get minus 4.9 over 256. That's for x squared here. I then get 3 over 16x. So 3 over 16x. And then finally, plus 6. Perfect. So this here then is a quadratic equation, right? And in that case then, the skateboarder's path is a parabola. If you want to, you can make this look a little bit neater, right? So y is equal to, so that would be minus 49 over 2,560 x squared plus 3 over 16x plus 6. You don't have to do this, but it just makes it look a little bit neater. If we're being a little bit pedantic, there you go. So this here then, let's just make a note. So this here, this is a quadratic equation. So this is a quadratic equation. And therefore, in that case then, so therefore, the skateboarder's path is a parabola. Skateboarder's path is a parabola. Perfect. So that is essentially the first part of part D done, right? We've shown that the skateboarder's path is a parabola. What we also want to do here then is find the maximum height above ground level of the skateboarder. So what I'm going to do here then is differentiate equation 2. That would give me dy by dt. I then set that equal to 0 and solve for t. And then I take that value of t here and substitute that into my equation for y here, right? The height. Okay. So, like I said, right, let's just find dy by dt here. So, dy by dt should be nice and straightforward. Just go term by term here. So, dy by dt then, what do I get here? It's going to be minus 4.9 times 2, so that's minus 9.8. So I get minus 9.8t there. Like so. And then the 3t here, that differentiates to give us plus 3. To get minus 9.8t plus 3 here. So we set this equal to 0. So let's just make a note here. Set dy by dt equal to 0. In that case then, 9.8t is equal to 3. And therefore then t is equal to 3 over 9.8. Which gives us, so that would be 15 over 49, right? So 15 over 49. And like we said then, we take this value t here and substitute that into equation 2 here. And what that's going to give us then is the maximum height above ground level. So substitute this value t here into equation 2. So what do I get here then? So y is equal to, get minus 4.9 times by, so I get 15 over 49 squared. 15 over 49 squared plus 3 lots of 15 over 49. And then finally, plus 6 here. Okay. So at this point here, right, just put all of this into your calculator. And if you do this correctly, then what you should get here is 6.46 there. Okay, so that's 6.46 meters there. And in that case, then let's just do that over here. So therefore, the max height, above ground level is simply 6.46 meters there. Okay. And there we have it. So Bosch, like you can see, part D was a little bit more work, but again, mathematically nothing too challenging, right? A little bit of differentiation, solving for t, and then just substituting that back into equation 2. Okay, so there we have it then. That gives us the solution to part D and the solution to question 8. Now for the next question here, question 9, we have a very typical exam style question. Now for this question here, then what we're given is y is equal to cos theta, where theta is measured in radians, and we want to differentiate from first principles to show that dy by d theta is equal to minus sine theta. And what we're told here then is we can assume the following. So the formula for cos of a plus or minus b, and also as h tends to 0, sine h over h tends to 1, and cos h minus 1 over h tends to 0. Now, what I've also included here in the top right corner is 2 results that are given in your formula book, and they're probably going to be quite useful as we work through this question. So let's just get started then. And what I always do here for any differentiation from first principles question is start by stating f of x and also f of x plus h here. Now, for this question then, our variable is theta, so it won't be f of x and f of x plus h, it would be f of theta and f of theta plus h, but that doesn't really make a difference, right? So in that case then, f of theta here. What is that? That is cos theta, right? So cos theta, and then for f of theta plus h, that is simply cos of theta plus h. Okay? And at this point here, all we now need to do then is just use this result here. So the derivative then, so d by d theta of cos theta from first principles then is equal to the limit. So this is the limit as h tends to 0 of f of x plus h. So replacing x with theta here, we get cos of theta plus h. So cos of theta plus h minus f of x, so minus f of theta, which is cos theta. So minus cos theta there, and this here then is all over h. Okay? Now for the next step here then, we now need to use this result here on cos of theta plus h. So again, it's the limit as h tends to 0 for cos of theta plus h. So cos of theta plus h using this result here then is cos theta cos h minus, so just be careful you get that the right way around, so minus then sine theta sine h. So cos theta cos h minus sine theta sine h. Okay? Don't forget as well the minus cos theta here. Very easy to forget that. Minus cos theta. And all of this here is all over h. Okay? Now, what I want to do here is start to work towards these two expressions here. So sine h over h and also cos h minus 1 over h. If we can obtain both of these here, then we're cooking, right? So how do we work towards these? Well, what I'm going to do then is group the cos thetas together here. And I'm also going to split this up as two separate fractions. Okay. So what I've got here then is the limit as h tends to 0. And for this part here, let's just put all of this inside a square bracket. So what I get here then is cos theta cos h minus cos theta. So minus cos theta. And all of this here is over h. So like we just said then, I want to split this up into two separate fractions. And then what I get here is minus sine theta sine h over h. So minus sine theta sine h all over h. Okay? Close those brackets like so. So up to now, everything's looking good. So what I'm going to do here then is factor out a cos theta from this left-hand term here. Again, I've got the limit as h tends to 0 of, so what have we got here then? We get cos theta outside, so inside then what do we get here? We get cos h minus 1. So cos h minus 1, and all of this here is over h. For this part here then, let's just essentially factor out the sine theta, right? So minus sine theta times by, so we'll write that as sine h over h. Okay. And what you can start to see then is we've obtained these two results here, right? Or pretty close to obtaining both of these results. I've got sine h over h here. I've also got cos h minus 1 over h here, just timesing them by cos theta and sine theta respectively. Now to continue here, what I'm going to do then is take this limit here and use linearity. And what I can do then is write that as two separate limits. And what I'm also going to do at the same time is take the cos theta and the sine theta outside these separate limits. So putting that all together then, what I get here is the following. So like we just said then, take the cos theta outside the first limit. So we get cos theta times the limit as h tends to 0 of, so it's cos h minus 1 over h. So cos h minus 1 over h. And again, take the sine theta outside the remaining limits. We get minus sine theta. So minus sine theta times the limit as h tends to 0 of sine h over h. So sine h over h here. Okay, perfect. Because what I can do now is use this fact here. So as h tends to 0, this one here, this limit tends to 1, and this limit here tends to 0. So using, let's just call this 2 here. So using 2 then, what we obtain here then is that cos theta is multiplied by 0. So it's cos theta times 0 minus then sine theta times by 1. Well, cos theta times 0 is just 0, minus sine theta times 1 just gives us minus sine theta there. So we obtain minus sine theta, and this here then is for the derivative of cos theta with respect to theta, right? So therefore, dy by d theta is equal to minus sine theta, exactly as we required, right? So as required there, and question complete. Okay, so there we have it then. Now, just a quick word of warning here. This was for y equals cos theta. Make sure that you can also do the same here then for y equals sine theta or y equals sine x, right? Both of these are quite common in, occurring on the A-level maths papers. So again, just make sure that you're confident with both of these examples here. Okay, so there we have it then. That gives us the solution here to question 9. Now for question 10, then we have the straight line L1, which has x-intercept 4 and has gradient m. So for the first part of this question, part A, we want to show that the equation of L1 can be given as follows. So for part A then, hopefully nice and straightforward here. We can do this in one of two ways. We can either just use y equals mx plus c, or alternatively here, I think this is the better way for this question, is to use y minus y1 is equal to m times x minus x1. So for this question here, just in case you can't see it, my x1 and y1 here are given by, given by this fact here, right? That the x-intercept is 4. What that tells us then is we have the point 4, 0 here, okay, for this straight line. So in that case then, x1 here is 4 and y1 is 0. And of course, we're given that the gradient is m here. So if we pull that all together then, what I get here is y minus 0 is equal to m times x minus 4. And in that case then, y minus 0 is equal to m times x minus 4. Well, that just simplifies to give us y is equal to m times x minus 4, exactly as we require, right? So as required there, and there we have it. So happy days, nice and straightforward for part A. Now for part B then, this is where things start to get a little bit more difficult, but again, hopefully nothing too challenging. So what I've got here then is the straight line L2 with this equation here, and the straight line L2 with this equation here meets the line L1 at the point P. So we want to show then that the coordinates of P are given as follows. So what I've got here then is the equation for L1. So that's for L1 there. And this equation here is for L2. So because they're both y equals here, what I can simply do here then is just equate the right-hand side for both of these equations. Okay. In that case then, m bracket x minus 4 is equal to 3x plus 1. Okay, so to begin with here, let's just expand the left-hand side to get mx minus 4m is equal to 3x plus 1. Okay, and what we want to do here then is rearrange and make x the subject. And once we do that, we can obviously just go on to find y then as well. So let's just take the 3x here over to the other side, and we'll do the same then with the minus 4m here. So what I'm going to do here then is subtract 3x off both sides and also add 4m to both sides as well. So we get mx minus 3x, like so, is equal to 4m plus 1. Okay. As you can start to see then, things are starting to look pretty good, right? I've got the 4m plus 1 here. I notice I've got the 4m plus 1 there. So let's just keep going here. Now on the left-hand side then, let's just factor out the x here. So we get x bracket m minus 3. Again, this is looking good, right? I've got the m minus 3 here as well for my denominators. And this here then is equal to 4m plus 1. To finish with then, let's just divide both sides by m minus 3. What we obtain here then is x is equal to 4m plus 1. So 4m plus 1 all over m minus 3 there. Okay, perfect. That's exactly what we want here. We're not finished, right? Because we also want the y coordinate here as well then for the point of intersection, the point P. So we know then that, well, based on L2 here, this has equation y equals 3x plus 1. So using L2 then, okay, so using L2 here, what do we obtain then? So y is equal to 3 lots of this. So 3 lots of 4m plus 1 all over m minus 3. Like so, okay? And don't forget the plus 1 as well, of course. So if I expand here, I get 3 lots of 4m plus 1 over m minus 3. So 3 lots of 4m plus 1 all over m minus 3 plus 1. So let's get all of this here over a common denominator. So if we do that then, I get 3 lots of 4m plus 1 plus m minus 3 is all over m minus 3. Okay? So my numerator here then would simplify, I get 12m plus 3. Get 12m plus 3. That's this part here. I've also got plus m minus 3. Plus m minus 3 all over m minus 3. We are starting to run out of room here, so let's just keep going. Hopefully we can just about finish this. So I get 13m, this plus 3 and this minus 3 just cancel, right? So therefore what I get here then is that y is equal to 13m all over m minus 3 there. Okay, again, exactly as we required. So therefore then, I'll just do this underneath then. So therefore, the coordinates of P are simply given as 4m plus 1 all over m minus 3. Then for my y coordinate here, I got 13m over m minus 3. So 13m over m minus 3 as required, right? We've shown that there, and there we have it. So as required, perfect. Okay, another 4 marks in the bag there. Good stuff. But the issue here is I don't have much room now to finish part C and part D. So what I'm going to quickly do here is pause the video, clear the screen, and then we can have a go at answering part C and part D. So as we can see then, we've now cleared the screen, right? So let's just have a go then at part C and part D here. Now, starting off with part C then, what do we want to do here? Well, we're told that the point Q also lies on the line at L1 with the following coordinates. And we want to show then that the distance PQ is given as follows. And this here looks a little bit grim, right? So let's just start to work through part C, and hopefully it's not quite as grim as this here would suggest. So I want the distance PQ. Okay, so the distance PQ. Now for the distance PQ then, this is equal to the square root here of the following. So I do x2 minus x1 all squared plus y2 minus y1 all squared. So what I get here then is 4m minus 1 all over m minus 3 minus then 4m plus 1 over m minus 3. So 4m plus 1 all over m minus 3. Like we said, right, we take the square here of this full expression, or we square this full expression, I should say, plus then, and all we now need to do here is just do the same, right, with the y coordinate. So I get 11m. So 11m over m minus 3 minus then 13m over m minus 3. So 13m over m minus 3. Okay, and again, we square this full expression, like so there. Now this here does not look nice at all, but the nice thing here then is for these two differences, right, they're both over a common denominator of m minus 3. So let's just simplify here both of these individual brackets first before we do any squaring. So what I've got here then is the square root of, so 4m minus 1 minus 4m plus 1. So the 4m's here just cancel. I get minus 1 minus 1. I get minus 2 all over m minus 3. And we square this here. Okay, that's just this here simplified. And if we now do the same then for the y coordinates here, 11m minus 13m, that gives us minus 2m. I've got plus minus 2m all over m minus 3. And again, this is all squared. Okay, that is supposed to be a 2 there. Hopefully that looks more like a 2 than a 1. So at this point here then, it's pretty straightforward, right? Just square both of these individual brackets. So we get the square root then of, so what do I get here? So minus 2 squared is 4. So I get 4 over, this is m minus 3 all squared. Like so. This here then gives me 4m squared over m minus 3 squared. So plus 4m squared over m minus 3 all squared. And I've got my brackets there. There we go. And again, these are over a common denominator, so we can just write this here as the square root then of, so I get 4 plus 4m squared all over m minus 3. So m minus 3 all squared. And at this point here then, we're pretty close to the desired result, right? So all I now need to do here is just factor out the 4 within the numerator and then just expand here for my denominator. So what I get here then is the square root of, so 4 lots of 1 plus m squared there, like so. And now for the denominator here then, just expand this out, right? So I get m squared. I get minus 3m and another minus 3m, so that's minus 6m. Perfect. And then minus 3 times minus 3, that gives me plus 9. Exactly as required. Beautiful. Okay, so there we have it. That gives us the solution to part C. And now for the very last part then of question 10 here, we have part D. Now for part D then, what do we want to do here? Well, we're given that m is an integer and that the distance PQ is 2 root 17. We want to find the value of m here. So if the distance PQ is 2 root 17, all I need to do here then is just equate this and 2 root 17. So let's just do that then to begin with. I've got 4 times 1 plus m squared all over m squared minus 6m plus 9. And this here then is equal to 2 root 17. Okay. Now, given that we have the square root here then of this full expression, well, just to make life a little bit easier here, let's just square both sides then. If I square the left-hand side, well, I just get whatever's underneath the square root here. I get 4 times 1 plus m squared all over. So we get m squared minus 6m plus 9. Okay. And this here then is equal to 2 root 17 all squared. So that's 4 times 17, which gives us 68, right? So 68 there. So we want to solve for m here. So let's just start then by timing through by this quadratic here. In other words, the denominator. So I get 68 times by m squared minus 6m plus 9, like so. This here then is equal to 4 lots of 1 plus m squared. Okay. Now, straight away, what I can do here then is just divide through by 4. So that just goes. This here then becomes 17. So if I expand this out here, I get 17m squared. So 17m squared, 17 times minus 6 there, that gives me minus 102m. And then finally 17 times 9 there, that gives me 153. And this here then is equal to 1 plus m squared. So let's just make the right hand side here then equal to 0, right? So just subtract m squared and 1 off both sides. So what I get here then is 16m squared minus 102m, we can't do anything with that. Minus 102m, and then 153 minus 1 gives us 152 there. Okay. And at this point here then, all I need to do, right, is just solve this quadratic here. What you can also do if you want to is just divide through by 2. You don't have to, you could just put this straight into your calculator here, but if I just divide through by 2, you get 8m squared, I get minus 51m, and then finally plus 76 is equal to 0. And at this point here, we can't simplify this any further, so just put this here into your calculator. And if you do this correctly then, what you should find here is we get 8m minus 19 times by m minus 4. And this here then is equal to 0. And at this point here then, we get two solutions for m. As we can see then, let me just do this over here. I can see then that am is equal to 19, so m is equal to 19 over 8. And we also have that m is equal to 4. Now, at the beginning of part D then, we're given that m is an integer. So we know then that m here cannot be this as my solution, right? So we cross that one off. And in that case then, m is equal to 4 there. And there we have it then. So not the easiest of questions here, especially for what is normally quite a straightforward topic, right? It's just straight lines and coordinate geometry. But hopefully you did enjoy that question and hopefully you got all of the marks, right? So there we have it. That gives us the solution to question 10. So let's get started then with question 11 here. So for the first part of question 11, part A, we want to show that this summation here is equal to lambda, where lambda is an integer to be found. 3 marks for this, and can be quite tricky if you've never seen an example like this before. So let's take a look at this together. Now for part A then, what have I got here? So we've got the summation of log, this is log of n plus 4 over n plus 3, base 3, from n equals 1 to 104. And we need to show that this summation here is equal to lambda, where lambda here is just some integer. Now, for a question like this, if you're not really too sure where to begin, what I'd say then is start by listing the first few terms of this summation here, and also the last few terms of the summation. So for example, then when n equals 1 here, what do we get? When n equals 1 here, we get log of, so that's going to be 1 plus 4, which is 5, over 1 plus 3, which is 4. So I get log of 5 over 4, so 5 over 4, base 3. When n equals 2, what do we get here? So we're going to get log, this time now, of 6 over 5, base 3. One more example here then. So when n equals 3, what we get then is, so I get log of 7 over 6, base 3. Okay. And if we think about the last few terms here, so for the last few terms here, what would we get then? So for n equals 102, this would be log of, it's going to be 102 plus 4, so that's 106. So 106 over 105. Again, base 3. When n equals 103, what we get here then is log of, so we get 107 over 106, again, base 3. And then finally here, when n equals 104, we get log of, so we get 108 all over 107. And again, base 3 here. So you might be wondering then, why did we even bother listing these terms here? Well, let's just go back to this summation here then for a moment. So what I've got here then is the summation of log of n plus 4 over n plus 3 base 3 from n equals 1 to 104. Okay. So this here then is equal to log of 5 over 4 base 3 plus log of 6 over 5 base 3 plus log of 7 over 6 base 3 plus so on and so on, all the way up to the last few terms here. So for example then, I get log of 5 over 4 base 3 plus log of 6 over 5 base 3 plus so on and so on up to the last few terms here, right? So for example then, log of 107 over 106 base 3. And then finally my very last term here, which unfortunately I've just run out of room, but I'll write underneath then. That is log of 108 over 107. Again, base 3. Okay. Now, you might be able to see straight away what we need to do here. If not, then just think about using the laws of logarithms here. So what I've got here then is a log plus another log plus another log plus another log, quite a few times, right? So what I can do then is use the laws of logarithms here. So we can write this as a single logarithm. So what I've got here then is log base 3 of the following. So I've got, for example, 5 over 4. So 5 over 4 times by 6 over 5 times by 7 over 6. And clearly this just keeps going on and on and on, all the way up then to the last few terms here. That would be 106 over 105 times by 107 over 106. Again, apologies, I've not left much room here, but hopefully you can just about make out what I'm going to write here. And then finally 108 over 107. Perfect. Okay. And at this point here, I can now see what's going to happen, right? Because I've got 5 over 4 times 6 over 5. 5s will just cancel here. I've got 6 over 5 times 7 over 6. The 6s will just cancel. The 7 would cancel with the next term here, so on and so on. This 106 here cancels with this 106. The 105 would cancel with the fraction before that. This 107 cancels with this 107 here. In that case, then what I get left with here is log base 3 of, we'll get 108 over 4. They're the only things that are actually remaining here, right? We'll get 108 over 4. So 108 over 4 is 27. I get log 27 base 3, which is equal to 3, right? And in that case then, lambda here, as it said, right, is an integer, and lambda is equal to 3. Okay, beautiful. I really like that question. Hopefully you did manage it, but just in case you couldn't write, just, take a methodical approach here. For questions like this as well, if you're not too sure where to begin with a summation type question, just list the first few terms and the last few terms. I do think it helps to kind of illustrate the summation that you're dealing with and hopefully spot the pattern with that summation. Okay, so there we have it then. That gives us the solution to part A of this question. as we can see, right, we don't have a whole lot of room here to answer part B and part C. So let me just quickly pause the video, clear the screen, and then we can have a go at part B and part C. So we've cleared the screen now, so let's just have a go then at part B and part C here. Now for part B then, what we're given here is a geometric series given by the following. So 3 plus 6x plus 12x squared plus so on and so on. We're then told that this series is convergent, and for part B then, we want to write down the range of possible values of x here. So for part B then, what I've got here is this geometric series. So 3 plus 6x plus 12x squared plus so on and so on. Okay. Now, straight away then, what I can see here is my common ratio r. So r here is equal to 2x, right? 3 times 2x is 6x, 6x times 2x is 12x squared, so on and so on. Okay. Now, what's important here is that we're told that this series is convergent. So why is that important then? Well, if convergent, let's just make a note here. So if convergent, then the modulus here of our common ratio r is strictly less than 1. Okay. So for this geometric series here, r is equal to 2x. So in that case, then the modulus here of 2x is strictly less than 1. So in other words, 2x is between -1 and 1. And in that case, then x here, or the modulus of x, I should say, is strictly less than a half. So in other words, x is between -1/2 and 1/2 there. Okay. So there we have it. That gives us the solution to part B. And now for the very last part then, part C here. What we're given here is the following. So the summation here of 3 times 2x to the power of r minus 1 from r equals 1 to infinity is equal to 4. So for part C then, we want to find the value of x. So what you need to recognize here then is this. So in fact, ignore the summation for now. This part here, so 3 times 2x to the power of r minus 1 is simply this here. It's this geometric series, right? So what I'm being told here is the sum to infinity of this geometric series here is equal to 4. So the sum to infinity is equal to 4. So what I know here then is A, my first term is 3, my common ratio is 2x, and the sum to infinity here is 4, right? But the sum to infinity, we calculate that as A over 1 minus r. Okay. So what I get here then is 3 over 1 minus 2x is equal to 4. Okay. As we're told here then for part C. So at this point here, really, to be honest, quite a nice, easy part of the question, right? All you need to do here then is just solve for x. So times 3 by 1 minus 2x on both sides here. In that case, then I get 4 times 1 minus 2x is equal to 3. Expand here if you want to, or you can just divide 3 by 4. Either's fine. Let's get 4 minus 8x is equal to 3. Take this minus 8x over to the other side, subtract 3 off both sides. So what I get here then is 8x is equal to 1. And then finally here, just divide both sides by 8. We obtain that x is equal to 1 over 8. Okay. And there we have it then. So like we said, part C is actually quite deceptively easy, to be honest, as long as you understand what this notation here is actually representing. Okay. So there we have it then. So that gives the solution to part C. This here was the solution to part B. And that gives us the solution to question 11. So for the next question here, question 12, we have a question on everybody's favorite topic, right, of integration by substitution. So for this question here, then we want to use this substitution to show that this integral here is equal to a plus b ln 2, where a and b are constants to be found. So pretty standard stuff, right? So to begin with here, I've got this substitution. So u is equal to e to the x minus 1. Okay. Now, what I always like to do here with an integration by substitution is basically lay the groundwork here, right? Because I need a few different things. So at some point, we'll need dx here. So to obtain dx, right, we need to differentiate u with respect to x. So du by dx then, that is simply e to the x. So in that case then, dx here. So dx then is simply times root by dx. I've got e to the x dx. Divide both sides by e to the x. So that's du over e to the x. And also, at some point here, right, we'll need e to the x as well. Again, we can see it with dx here and also with my numerator. So let's just rearrange here as well. So e to the x then, nice and straightforward here. That's simply u plus 1, right? And in that case, then we can rewrite dx here using e to the x is equal to u plus 1. So dx then is du all over u plus 1. Okay. And I think at this point here then, we've now got everything that we need then to evaluate this integral here. So let's just start then by rewriting the integrand here. That's the thing that we want to integrate. So let's just do it underneath here. I've got the integral here then of, so if we start off with the numerator here then, I've got 2e to the 4x. So let's just split that up here then into two different parts. That's 2 times e to the x to the power of 4. Okay. So e to the x then, as we've just obtained here, is u plus 1. So what I've got then is 2 times u plus 1 all to the power of 4. Okay. This here then is my numerator. That's 2e to the 4x. Nice and straightforward, right? But the denominator here, even easier, right? That's just e to the x minus 1, which is simply u. So that's over u here. And what I've also got to finish with here then is dx. Now dx then is du over e to the x, which is just the same as du over u plus 1. We've got du all over u plus 1. Okay. Now hopefully you can see straight away then that this u plus 1 to the 4, we can reduce that to a power of 3 and cancel with this u plus 1 here, like so. So what I've got then is the integral here of, so it's 2 bracket u plus 1, the power of 3 all over u du. Okay. Now, don't worry, I haven't forgot the limits here. There's two ways to deal with the limits. You can either just replace these limits here based on u equals e to the x minus 1. That's absolutely fine. Or what you can also do here is keep the original limits, and then when we use back substitution a little bit later on, we go back to the original limits. Either's fine. I personally prefer to keep the original limits, so that's what I'll do here as I work through this question. Okay. So what I'm going to do here then is use linearity and take the 2 outside the integral. So what I've got here then is 2 lots of the integral here of, so it's u plus 1 cubed over u du, like so. At this point here then, let's evaluate u plus 1 cubed. You can just use the binomial expansion if you want, or just do it by hand, u plus 1 cubed. Either way then, what I should get here is u cubed 3u squared plus 3u plus 1. Okay. So what I've got here then is 2 lots of the integral here. And I do appreciate that I'm showing each individual step here. You could probably skip a couple of these steps, right? I'm going into quite a bit of detail. But what I'm going to get here then is u cubed plus 3u squared plus 3u plus 1 all over u. Okay? And again, don't forget du here. We are integrating with respect to u. So let's just simplify the integrand here then by dividing each term by u. So what I get here then is 2 lots of the integral then of, so u cubed over u, that's u squared. So I get u squared here. So u squared 3u squared over, so 3u squared over u, sorry, that is 3u plus 3u. 3u over u, that would just give me plus 3. I've also got 1 over u, which is going to simply be 1 over u or u to the minus 1, whichever you prefer. So plus 1 over u and also plus 3 there. Okay, and again, integrating here with respect to u. So at this point here then, let's just evaluate this integral here. Nice and straightforward, right? Just basic A-level maths integration at this point. So I get two lots then of, so u squared, we integrate with respect to u here, add 1 to the power, divide by the new power. So I get u cubed over 3. 3u then, again, add 1 to the power, divide by the new power. So I get 3u squared, so plus 3u squared over 2. So 1 over u, that would integrate here to give me ln u. So ln u there. And then finally the 3 here, that would integrate to give me 3u. So plus 3u there. Okay. And now, if we use reverse substitution here then, where u is equal to e to the x minus 1, what I get here then is two lots of, so u cubed, so that is e to the x minus 1 cubed. So e to the x minus 1 cubed, that's over 3, plus 3 lots then of e to the x minus 1 squared, and that is all over 2, plus ln of u here, which is, again, e to the x minus 1. So ln of e to the x minus 1. And then finally here, we have 3u. So 3 lots of e to the x minus 1. Perfect. Okay. So now that I've replaced u here with e to the x minus 1, right, we've used reverse substitution here. I now go back to the original limits, right, because it's now in terms of e to the x again here. Okay, so ln 3 and ln 5. Okay, so to deal with these limits here, let's go all the way to the top here. So again, don't forget, nice and straightforward, right? We start with the upper limit, subtract the lower limit. So I get two lots then of, so two lots here of, so e to the ln 5 is simply 5. So 5 minus 1, which is 4. So I get 4 cubed over 3. So I get 4 cubed over 3. 4 cubed over 3. This here again is going to be e to the ln 5. So that's 5 minus 1. So I get 4. 4 squared is 16. Times that by 3 and then divide by 2. So 3 lots of 4 squared. 3 lots of 4 squared. Divide by 2. Looking at this here, I'm not going to have a whole lot of room. We'll try and make it. So 3 lots of 4 squared over 2, plus ln of 4 here, plus ln 4. And then finally, 3 lots of 4. 3 lots of 4. Okay. So this here then, this is my upper limit. So let me just get rid of this arrow here, just so I don't cause any confusion. So I've just kind of took it to the top here. Let me just rewrite this as well, so it looks a little bit neater. So this is 2 lots of following. Okay, so this here is our upper limit. We now subtract the lower limit here. So minus them. So with ln 3 as my lower limit, what do I get here? So e to ln 3 is 3. So I get 3 minus 1, which is 2. So I get 2 cubed over 3. So minus them. Get 2 cubed over 3. And this will certainly be tight. Hopefully we might just about make it. So what do I then get? Can't speak anymore. So 3 times 2 squared. So plus 3 times 2 squared over 2. I get ln. So that's e to ln 3, which is 3 minus 1. So ln 2. So plus ln 2. And then finally here, 3 times 2. Plus 3 times 2 there. Apologies, this is starting to look a little bit messy here, given that I am starting to go into the original line of working here. So let me just quickly cross this off just so it doesn't cause any confusion as well. Let's just get rid of this and this. Okay, so I've got a little bit more room here to work through the question. So dealing with these limits here then, well, we've evaluated the limits, right? Just need to evaluate each one here using our calculator. Okay. So what I've done here then is put these into my calculator and also times through by 2 at the same time. So I get 2 lots of this here minus 2 lots of this here. Okay. Or you can just do the full thing here in your calculator, times by 2. It really doesn't matter. Either way, you'll get the same answer, right? So what I'm going to get here then for the first bracket, once I times through by 2, is I get 344 over 3 plus 2 ln 4. Okay, this here then is my upper limit here times by 2. We then subtract then the lower limit here times by 2. So I then get minus here, a8 over 3 minus a8 over 3 minus ln 2. Sorry, minus 2 ln 2, sorry. Over here we times through by 2 there. Sorry. So we're nearly there now. This question has fried my brain. And recording all these questions in a row is always a bit of a tedious job, but we're nearly there. So let's just keep going then. So 344 over 3 minus 88 over 3. Well, that just gives me then 256 over 3. So 256 over 3. Perfect. I've also got 2 ln 4 minus 2 ln 2. So what I get there then is 2 ln of 4 over 2, which is 2. So I get 2 ln 2, right? Just basic laws of logarithms. Okay. And at this point here then, notice now it's in this form here. So 256 over 3 is A, and B here is 2. So to finish with then, let's just state the values of A and B. I'll do it in a different color just to make it clear. So therefore A is 256 over 3. So 256 over 3. And for B here, B is simply 2 there. Okay. And there we have it then. So again, everybody's favorite topic, right? Integration by substitution. But hopefully this work solution here has helped illustrate the concept then of integration by substitution. So that gives us the solution here to question 12. Now for the penultimate question here, question 13, we have a question on trigonometry. Now we're given that 3 cos of x plus 70 degrees is equal to sine of x plus 20 degrees. And for the first part of the question, then part A, we want to show without using a calculator that tan x is equal to a half tan 20. So how do we do this here? So for part A then, the only thing that we can really do here with this equation is just use the compound angle formula, right? We're going to use cos A plus B and also sine A plus B. So let's just do that here then. So I get 3 bracket. So using cos A plus B on cos x plus 70 degrees here, we obtain the following. So I get cos x cos 70 degrees minus then sine x sine 70 degrees. Okay, that's the left-hand side here. Now just applying the same then to the right-hand side, but obviously for sine of A plus B, what we get here then is the following. So I get sine x cos 20 degrees. So sine x cos 20 degrees. And also cos x sine of 20 degrees. Okay. So what I'm going to do here is group sine x on the left-hand side and cos x on the right-hand side here. So if I expand this out here then, I get 3 cos x cos 70 degrees minus 3 sine x sine 70 degrees. So, like we just said then, let's group the sine x terms on the left-hand side. So what I get here then is, so I get sine x, so sine x cos 20 degrees, plus 3 sine x sine 70 degrees, right? This term here. So plus 3 sine x sine 70 degrees. And then grouping the terms here for cos x on the right-hand side, what we get here then is 3 cos x. So 3 cos x cos 70 degrees minus then cos x sine 20 degrees. Okay. Now let's factor out the sine x on the left-hand side and cos x on the right-hand side. So starting with the left-hand side here, we get sine x bracket. So what do I get here then? So I'm going to get 3 sine 70 degrees. So 3 sine 70 degrees plus cos 20 degrees plus cos 20 degrees there. And now factoring out cos x on the right-hand side here. So I get cos x bracket. So what do we get here then? So we get 3 cos 70 degrees. So 3 cos 70 degrees minus sine 20 degrees. Minus sine 20 degrees there. Perfect. And at this point here then, we're going to use this relationship here. So I'm going to use them. The fact that sine of 70 degrees here. So sine of 70 degrees here is equal to cos. So cos of 20 degrees. And also the fact that cos of 70 degrees here. So cos of 70 degrees is equal to sine of 20 degrees. Okay. So in that case here then, what would we get? So sine of 70 degrees is equal to cos of 20 degrees here. Let me just divide both sides by cos x first. Probably easier to just divide both sides by cos x. So in that case then, I get tan x on the left-hand side. So tan x bracket, I won't change anything yet. I'm using this relationship. So 3 sine 70 degrees. So 3 sine 70 degrees plus cos of 20 degrees is equal to, so we divided through by cos x here, so we just get left with this bracket. So 3 cos of 70 degrees minus sine 20 degrees. Okay. Now we just want tan x here, right? We want to show that tan x is equal to a half tan 20. So let's just divide both sides by this here. So therefore tan x is equal to, so I get 3 cos 70 degrees minus sine 20 degrees. So 3 cos 70 degrees minus sine 20 degrees. And this is all over then 3 sine 70 degrees. So 3 sine 70 degrees plus cos 20 degrees, right? Plus cos 20 degrees here. Now, if we need to obtain tan here on the right-hand side, then at some point, my numerator here should be sine, or in terms of sine, and my denominator here should be in terms of cosine. So now let's use this relationship here. So in that case then, if we've got 3 cos of 70 degrees here, we can use this relationship then. So this here is just 3 sine 20 minus sine 20. So I get 3 sine 20 degrees minus sine 20 degrees. Apologies, by the way, it's a little bit close to the edge here, but hopefully you can just about read this. And then for the denominator here, right, like we just said, we want this in terms of cosine. So 3 sine 70 degrees, we can write that as 3 cos 20 degrees, right? I've got 3 cos 20 degrees plus cos 20 degrees. Oops, so plus cos 20 degrees there. Okay. And then finally to finish with here, let's just simplify. So I get 2 sine 20 for my numerator. So 2 sine 20 degrees for my numerator. For my denominator here, I get 4 cos 20 degrees. So 4 cos 20 degrees. 2 over 4 is a half. Sine 20 degrees over cos 20 degrees is tan 20 degrees. So we obtain then a half tan 20 degrees exactly as required. So therefore tan x then, so tan x is equal to a half tan 20 as required. Perfect. So, as you can see then, quite a lot of working just for part A. We took up a lot of screens, so let me just quickly pause the video here, clear the screen, and then we can have a go at answering part B. So as we can see then, we've now cleared the screen here, so let's have a go then at answering part B. So for part B then, it says, hence solve for theta between 0 and 180 degrees, 3 cos 4 theta is equal to sine of 4 theta minus 50 degrees. I'm going to give our answers here to 1 decimal place. Now for part B then, let's just do this at the top here. We somehow need to link this here, so this here, and the equation in part B. So what we want here, so just notice then this is 3 cos of x plus 70 degrees is equal to sine of x plus 20 degrees. That's pretty similar to this here, right? There's obviously a difference, but it's pretty close. So what we want here then is something of this form. So we want here 3 cos of x plus 70 degrees is equal to sine of x plus 20 degrees. Okay. And we're going to need to use this and this here, right? So what I'm going to do here is use a substitution, because what I want here then is the argument of our trig functions here to be equal to these arguments here. So in that case then, what I'm going to do here is let x plus 70 degrees, let's write that as x plus 70, be equal to 4 theta here, right? Just equating these two arguments here. And what we're going to do then is rearrange here and make x a subject. So x then is equal to 4 theta minus 70. Okay. Why is that important then? Well, what I can do here is replace x with this here, 4 theta minus 70 degrees. Okay. So in that case then, tan, so it's tan x here, where x is 4 theta minus 70 degrees. So that's tan of 4 theta minus 70 degrees here. And this here then is equal to a half tan 20. Okay, so at this point here, pretty straightforward, right? All we now need to do then is take tan inverse of both sides. On the left-hand side, then we simply get 4 theta minus 70 is equal to tan inverse of a half tan 20 degrees. So I get tan inverse then of a half tan 20 degrees. Okay, so what I get here then for 4 theta minus 70, so 4 theta minus 70 degrees is equal to, so I'm going to get quite a few solutions here, right? Because my domain is pretty small, 0 to 180 degrees, but because we're solving for 4 theta here, the solutions, right, are going to be eventually dividing through by 4. We're probably going to get quite a lot of solutions here within the domain. Okay, so to begin with then, if you do tan inverse of a half tan 20 degrees, I get 10.3 here. Okay, and that's to 1 decimal place. Now tan is periodic every 180 degrees, so just add 180 to this solution here, and that gives us the next solution, right? Get 190.3, sorry, degrees. Add another 180 to this, I get 370.3. Just keep going here. It would have been a little bit more useful to do this further to the left, so I could just put these in a straight line, but it doesn't matter too much. I'm also going to get 550. In fact, just to make this a little bit easier, what I'll do is I'll just rewrite this further to the left. I said I wasn't going to do that, but just so you can see the solutions here and how they line up quite nicely. So 4 theta minus 70. So apologies for this. Just want to make sure that it's neat and you can follow along quite nicely here. So like we said, then we get 10.3 here. I then get 190.3, so just simply add 180 to that. 190.3. I get 370.3. I get 550.3. And then at this point here, I'll do one more. So 730.3. Okay. I'll stop for now. We might need more solutions. We might need less, but for now, I'll just leave it at this point here. Okay. Now we want to solve for theta here. So for the next step, then we simply add 70 degrees to all of these solutions here. So 4 theta is equal to 80.3. Again, just keep adding 70 to each one of these solutions here. So I get 260.3. We then get 440.3. We then get 620.3. And then finally here, 800.3. Okay. And then finally, right, we just want theta here. So just divide all of these solutions here by 4. So therefore, theta is equal to, so 80.3 divided by 4. I get 20.1 there. Okay. 260.3 divided by 4. I get 65.1 degree. Just keep going here, right? So just divide each one by 4. At this point, all of these solutions are still within the domain here for theta, so that's absolutely fine. I then get 110.1 degrees. I then get 155. So 155.1 degrees. And then clearly for the next one here, right, once I divide through by 4, this would fall outside the domain. I'll just state it anyway, but we'll omit it a little bit later on. We get 200.1 degrees there, but clearly this is greater than 180 degrees. So we omit that solution there. Okay. So there we have it then. So let me just quickly highlight this here. So the solution then, or solutions, I should say, for theta are as follows. Let's box these off in red here. Okay, so you should obtain the following solutions then for theta. So 20.1, 65.1, 110.1, and then finally 155.1 degrees there. Okay, and there we have it then. So that gives us the solution here to question 13. And then finally, to finish with here, we have the very last question, question 14. And as we can see then for question 14 here, there's quite a few different things going on. So let's just go step by step here. So for part A then, well, let's just begin by actually reading the question, right? It's always a good step. So the volume of a spherical balloon with radius r centimeters is given by the following. You should obviously recognize that, right? And then for the first part of the question, part A, what we want to do here then is find dv by dr. So 1 mark, nice and straightforward, right? So dv by dr here, just differentiate v, this expression here, this equation, with respect to r. So what do I get here then? So I get 4 over 3 times by 3. Just get 4, reduce the power of r here by 1. So I get 4 pi r squared. Bosh. Nice and easy, right? 4 pi r squared there. That's all we need. Just 1 mark in the bag there. Now for the next part of this question, part B, again, let's just read the question as we go. So at time t seconds, the volume of the balloon is increasing according to the following differential equation here. We're given that v is equal to 0 when t is equal to 0. So for part B then, by solving the differential equation, we want to show the following. Right, so what I've got here then is dv by dt. Let me just start by writing this down here. That's 1,200 all over 3t plus 2 squared. Okay, so what I need to do here then is solve this differential equation here. So to do that, what I'm going to do then is integrate both sides here with respect to t. Okay, so do it underneath then, just because I don't have a lot of room there on that line. So integrate both sides here with respect to t. So I get dv by dt with respect to t is equal to the integral then of 1,200 all over 3t plus 2 all squared. Okay, and again, we're integrating here with respect to t. Now, for this differential equation here, right, we don't need to separate the variables, so just be slightly careful. We can just go straight into solving. Now, if I integrate dv by dt with respect to t here, that's going to simply give me v on the left-hand side. I get v here on the left-hand side. Now, for the right-hand side here, a little bit more complicated. The first thing that I'm going to do then is take the 1200 outside the integral using linearity. So v is equal to 1200 times the integral then of, so it's 1 all over 3t plus 2 all squared. Okay, and again, integrating here with respect to t. Now this here then, there's two ways to do this. You can go about this using substitution, or probably the easier way here is to just use the reverse chain rule, right? Now either method's fine if you want to use substitution, absolutely fine. It's probably just going to take you a little bit longer to, evaluate this integral here. But what I'll do then is I'll use the reverse chain rule here. So what I get then here is v. Oops, so v here. I made a mess of that. Let me try again. Apparently I can't write the letter v. English is hard. So v is equal to, let's give it another go. I get 1200 times by them. So what I get here is minus 1 all over 3 times 3t plus 2. Reduce the power by 1 here, right? So minus 1 over 3 times 3t plus 2. Okay, like so. And don't forget here as well, right? Plus c, our constant of integration. So if I simplify here, what I get then is that v is equal to, I get minus 1200 over 3 times 3t plus 2 plus c. Well, clearly we can simplify here, right? So what I get then is v is equal to, so I get minus 400. So minus 400 all over then 3t plus 2. Don't forget the plus here, plus c here as well. So plus c as well. Now, clearly then, we're not quite at this point here, the required form, right? So to obtain the required form here, what we're now going to do then is use this initial condition here. So v is equal to 0 when t is equal to 0. Let's just make a note here. So when t is equal to 0, v is also equal to 0. And using this initial condition here, then we can now solve for c. So 0, in fact, let me write this as if this is on the left-hand side. I get minus 400 all over then. So 3 times 0 is 0. So minus 400 over 2 plus c is equal to 0. Okay, I get minus 200 plus c is equal to 0. And in that case here then, c is equal to 200. Perfect. So in that case then, v here, let's just write this at the bottom. So therefore v is equal to, so I get c, which is 200. So 200 minus then 400 over 3t plus 2. So minus 400 over 3t plus 2. Let's times through, well, not times through, but let's get this over a common denominator, I should say. So if I do that here then, let's move this out of the way so I can actually see my screen here at the bottom. So what I'm going to get then, I'm going to get 600t, so times 200 by 3t plus 2, right? I get 600t plus 400 minus the original 400 here. And this is all over 3t plus 2, like so. The 400 and the minus 400, they just cancel. And what I get left with here then is that v is equal to 600t over 3t plus 2, exactly as we require. So 600t all over 3t plus 2 there, as required, right? So as required. Perfect. Okay. So there we have it then. That gives the solution to part B. Now, as we can see then, we took up the full screen here just to answer part B, right? So let me just quickly pause the video, clear the screen, and then we can have a go at part C, part D, and part E. So as we can see then, we've now cleared the screen here. So let's just have a go then at part C, part D, and part E here. Now starting off with part C then. So starting off with part C then, it says hence state the upper limit to the volume of the balloon. So for the upper limit to the volume of the balloon here, what we want to consider then is what happens to the volume as t tends to infinity here. Let's just make a note then. So as t tends to infinity here, what will happen then to the volume of the balloon? Well, we shouldn't ever really think about infinity as a number here. So I'm kind of breaking all the rules of maths, right? So what I'm going to get then is 600 times infinity over 3 times infinity plus 2. Now the plus 2 then is just negligible. It won't make a difference, right? So I get 600 infinity over 3 infinity. The infinities just cancel. Again, I'm just breaking all the laws of maths here. I get left with 600 over 3, which just gives me 200. So as t tends to infinity, 600t over 3t plus 2, this here then just tends to 200. Okay, so in that case then, let's just make a note here. So therefore, the upper limit, here, the upper limit to the volume of the balloon, is, so what we've got here then was 200, so this is 200 centimeters cubed, right? Because we're talking about volume here. Okay, so there we have it then. That gives us the solution to part C. Now for part D then, what do we want to do here? So we want to find the radius of the balloon when t equals 2, giving your answer in centimeters to 3 significant figures. Now, just a quick point here. Even if you couldn't show this result in part B, you can actually still go on to answer part C here, part D, and part E, right? Because they give you this result here. As long as you've got this result, we can go on to answer part C, part D, and part E, as long as we can answer part A, right? Which I would hope that everybody watching this video can answer part A. So let's just continue then. So what I need to do here to begin with is substitute t equals 2 into v here. So v, when t equals 2, well, what I obtain here then is v is equal to 600 times by 2 all over, I get 3 times 2 plus 2. Okay, we get 1,200 all over then 6 plus 2, which is 8. And then 1,200 divided by 8 here, that gives us 150. Okay, now we want to find the radius of the balloon here when t equals 2. So I know the volume. What I now need to do here is take this value here for the volume and set that equal then to 4 over 3 pi r cubed, and then just solve for r, right? So I get 4 over 3 pi r cubed is equal to 150. Like we just said, solve for r here. So solve for r. In that case here then, what do I get? Or what would I do? I'm going to get r is equal to the cube root then. I get the cube root here of, it's going to be 150 divided by 4 pi over 3. So 150 divided by 4 pi over 3. Just put this here into your calculator, right? Don't need to be anything fancy. If you do this correctly then, and again, just be slightly careful here. Make sure that you give your answer in centimeters to 3 significant figures here. What we get then is 3.30 centimeters, right? Perfect. So that gives me the solution there to part D. And then finally, to finish with here, we have the very last part to the very last question. So for part E then, it asks us to find the rate of increase of the radius of the balloon at t equals 2. Given our answer to 3 significant figures, we must also show all of our working and also state the units to our answer. So what we're looking for here, so what we want here then is dr by dt, right? We want dr by dt. So for dr by dt then, we can obtain this by using the following relationship. So this is for part E, by the way. Also, if I write that down. So dr by dt then, like we just said, can be obtained by using the following relationship. So dv by dt is equal to dv by dr times by dr by dt, right? Connected rates of change here. Now, we know then that dv by dt here is the following. We also know dv by dr, right? Because we established that in part A. So we're pretty much there now with part E, right? We just need to put all of this together. So at t equals 2, we also know that the radius here from part D, R here, is 3.30, right? We established that in the previous part of the question. So putting this all together then, what I've got here is 1,200 all over 3t plus 2 squared, like so, is equal to dv by dr, which we cleared the screen, but that was simply 4 pi r squared. So 4 pi r squared, let me times here by dr by dt. Okay, now at t equals 2, what I get here then is 1,200 over, so that's 6 plus 2, so we square that, so 8 squared, so 1,200 over 64. So let's just put this all together here then to finish with. So dr by dt then is equal to, so we get 1,200 over 8 squared, so 1,200 over 64. And I also need to divide here then by 4 pi r squared, and r here is 3.30. We times through then by, it's 1 all over 4 pi times 3.3 squared there. Okay, put all of this here then into your calculator, and if you do this correctly then, what you should find here is we get 0.137 there to 3 significant figures. That's the question asked for, right? And again, don't forget the units here. So my units then are centimeters per second. Like so. And there we have it. Perfect. So this here then is the solution to part E. So that gives us the solution to the very last question, question 14. And that brings us to the end of these video solutions here for this predicted paper. If you have made it all the way to the very end of this video, thank you so much for watching. I do appreciate that these videos are quite long, but hopefully you have found this predicted paper helpful in your upcoming A-level maths revision. As a final point here, all I want to say then is best of luck for the upcoming A-level maths exams. If you are looking for any further A-level maths revision, be sure to visit our website, AJMaths.co.uk. But other than that then, I don't really have anything else to add here. So as always, thank you so much for watching and best of luck with your upcoming A-level maths exams.